Christa McAuliffe was chosen to become the first teacher in space. She planned lessons she would broadcast from space to students around the world. Tragically, she was unable to complete her mission to bring space to schools as she was one of the 7 crew members who died in the Space Shuttle Challenger disaster in 1986. However, teachers turned astronauts Joe Acaba and Ricky Arnold finished her mission in tribute to her. Our education team have revisited Christa's lost lessons to share them with you at home. You can try these experiments yourselves and then see how they work in space.
This experiment is called the walking rainbow, and we're going to be finding out if black ink really is just black. To do our experiment today, we're going to need some kitchen roll or some coffee filter paper, some black pens, all of which are water soluble, some water, test tubes or glass jars or even just glasses, and also some scissors, preferably safety scissors. So the first thing you'll need to do is to cut strips out of the kitchen roll or the coffee filter paper, whichever it is that you're using. Make sure you have an adult to help you, and make sure that each of these strips is evenly cut to fit inside your tube or your jar. Now your strips are ready, you will need to take each of the pens separately and draw a thick line across the bottom. Make sure it's about 4 to 5 centimetres from the bottom of your piece of paper. Next thing you'll need to do is to add some water to those test tubes or glasses, about 3 centimetres full from the bottom. Now we're ready to start our experiment properly. What we need to do is take each of those strips that you've drawn on and pop them into your jar or your test tube, whichever it is that you're using. Let the water be absorbed up the paper, but make sure the black line doesn't go directly into the water. Notice how the water moves up the paper. Now look carefully at your black line. Is it still black? Is the ink just black, or are there other colours in it as well? What do you notice from your pens? Next, we're going to add the other strips into the test tubes or jars and see what happens to those. Are they all the same, or is each pen slightly different? You should notice there's a rainbow of colours, and this process of splitting the black ink into all its different colours is called chromatography, and it happens because some pigments are more soluble in water than others, so they get pulled further up the paper, giving us this lovely rainbow effect. We notice with our pens each one was slightly different, so may have had more of one colour than another. What do you notice with your pens? We'd love to see your results. These are the results from our experiments today. How do you think this might work in space? Do you think you get the same results? Scientists use the same process of chromatography to have a look at plants and to find the different pigments that are inside those as well. Maybe that's something you can try another day.
Hello, my name's Josh, and today I'm going to be talking about density. Now, density can be a tricky topic because it's kind of difficult to understand. Density basically explains how much stuff or matter is inside something. Now, that doesn't necessarily mean it's hollow or empty, but to have a little look at this, I've got a few things to try and help us out. For example, I've got 2 balls here which are roughly the same size, but one is more dense, has more stuff in it, than the other. Now, down here on Earth, we can use gravity to help showcase the differences. And that's because gravity affects more dense things more than less dense things, because, well, there's more stuff to grab. So we can demonstrate this by placing these balls in the water. If we place them in, we can see very different things happen. First of all, this ball here sinks, and that's telling us that it's being affected by gravity more, so it's being pulled down with more force, and therefore it must be more dense than the water that's in my glass. On the other hand, this ball here, well, this is floating, which is being affected less by gravity, and so it's sitting higher up on the surface. It must be less dense than the water. Now, these can be quite easy to work out because generally we can tell the difference between density by feeling how much weight they have. This is the effect that gravity has. But we can use this to test things that are a little bit more difficult. For example, over here I've got some more water, although this water's blue to make it stand out. It's not anything different. And I've also got some oil. Now, both of these are liquids and they feel kind of the same weight. It would be very difficult to work out which was denser. But using gravity and a simple test, we can find that out here today. So let's pour the oil into the water and see what happens. So I've poured some oil in, and we can see quite straight away that something quite remarkable happens. The oil is sitting on top of the water. It's floating, just like this ball, which tells us it must be less dense than the water that's beneath it. That's because gravity is pulling the water down with bigger effect than it is the oil, so one floats on top of the others. So this is a really simple test that we can do down here on Earth. Maybe you could try it at home. But this sort of thing starts to get a little bit different if we were to do it up in space. Maybe you can have a little think about what might happen if we were to do this in space where gravity wasn't having as much of an effect.
Hi, my name's Will, and today we're going to be looking at Newton's 3 laws of motion. These were first compiled in 1687, and they're rules that help us to explain why things move in some ways, but not in others. So let's start off with the first law of motion. Newton's first law states that an object will remain at rest or in constant motion unless an external force is applied to it. We can see this here with my ball. It's currently at rest, there is no external force being applied to it, so let's apply one. Here we go. Now, as I pat the ball, I've applied a force to it, so the ball's come to a rest because there are other external forces being applied to it, gravity and friction, which have worked to slow the ball down and bring it to a stop. But would this work differently in space? Newton's second law of motion explains how a force can accelerate an object, but the rate of acceleration will be affected either by the amount of force or the mass of the object itself. We can see this in action here with this simple demonstration. I have a silver tray, a piece of bungee cord, which I'm going to pull back to the edge of the table, let go, which will apply a force to the object. So, let's pull this back. So we saw the tray accelerate across the table, but now let's add a heavier tray. I've placed some plastic tubes inside the tray so the object has more mass, and I'm going to apply the same force. Let's see how this affects the object's acceleration. So we can see there that with the same force, the object with a higher mass accelerated slower than the one with lower mass. But let's now change the amount of force. So you can see there with more force, the object accelerated faster and travelled further. Newton's third law of motion explains that every action has an equal and opposite reaction. We can see this here with this balloon full of air, which I'm going to let go of. The force of the air leaving the balloon in this direction will propel the balloon in the opposite direction. So these are the 3 laws of motion. But would they work differently in space?
Hi, my name's Rob, and today I'm going to be talking about effervescence. Now, effervescence is what we call the presence of bubbles, so a gas, in a liquid. Think of a fizzy drink. When you open the top, you get bubbles rising up through it. That's carbon dioxide gas escaping from the drink. What we're going to have a look at is a different kind of gas inside a liquid. We're going to be using a fizzy tablet. What I've got here are 4 containers, all the same size, all containing the same amount of water. I'm going to drop different amount of a fizzy tablet into each one and time to see what the reaction is. Effervescence is the presence of bubbles in a liquid. It's evidence of a chemical reaction. We're going to start off with half a tablet. I'm going to drop that into our water and at the same time start our timer. Here we go. Now it's important to wait until the tablet has completely dissolved before you stop your timer. While you're doing this, make sure you look at the amount of bubbles that are being produced. Think about how that might be happening, and think about that for later on as well. That's going to be very important as we move along through the experiment. You might be able to see there quite a lot of bubbles appearing quite fast but also disappearing quite quickly. Looks like a reaction starting to come to an end. Less and less fizzy until finally only a few bubbles left. And there we go. So just under a minute there. Now we're going to try the same thing, but with just a quarter of a tablet, so half the amount. Think about this while you're watching. Does it produce the same amount of bubbles? And does the reaction last longer or less amount of time? So reset our timer and go. Might be able to see there, not as many bubbles being produced. Bubbles aren't as big. And it looks like our reaction's nearly finished. Just a little bit of our tablet left to go. And there it is, just a few seconds less. Now we're going to try exactly the same thing, starting with half a tablet, same amount of water, but this time in a sealed container that I'm going to give a little shake to. So, make sure we reset our timer, drop in our tablet, start, and put the lid on, and give it a little shake. Now this time, think about what's going to happen. Before, when the gas was being produced, it could escape through the top. What do you think is going to happen this time? Okay, slightly missed the end of that there. Took me by surprise a little bit, I'll be honest, but a lot less time that time. Now exactly the same thing. You'll notice that we've still got some of our tablet there, but this time with only a quarter of a tablet. And again, think about what happens. Does it take less time for the reaction to occur? Are there more or less bubbles? We'll very easily be able to see this time based on how high the top goes. So here we go. Tablet in, lid on, little shake, and go. And once again, a little bit of a jump. So there we have our 4 different tests for effervescence. But how do you think that might be different in space? Think about how maybe the bubbles would react differently in microgravity, and maybe think about what might happen to the rate of reaction in microgravity as well. Thank you very much.